This week, we're learning how to recognize chemical reactions. We're not only going to learn the parts of the reactions, we're also going to look for signs of chemical reactions. Now, a reaction has two parts. You have the reactant, and that's the part that undergoes reaction. So if you have A plus B produces C, A plus B are your reactants. They're before the arrow. The products are what is formed as a result of the chemical reaction. Now, if you're not sure if you see a chemical reaction or not, there are four signs of a chemical reaction. One is a formation of a gas. Another is a formation of a precipitate. Another is a color change. And the last is a temperature change. So whenever you have a cold pack and you crack it, and out comes the cold, that was a sign of a chemical reaction. You started the reaction when you cracked it. There's a color change. That is an example of a chemical reaction. Like, you know, when you're looking at meat, when it's gone bad, if you haven't cooked it yet, it gets this grayish color. Formation of a precipitate, if you've ever left milk in your refrigerator for too long and it got chunky, there's your precipitate. And the formation of a gas, whenever you are burning wood, you see the smoke come up. You have gas that's being emitted. Or whenever you do baking soda and vinegar together and it starts bubbling, that's another example. I want you to take a moment to pause and try to determine which are products and which are reactants on your own. When you're ready to check, come back and see if you're correct. All right, so we know reactants are before the arrow. So everything in blue is before the arrow. Products, I'm going to circle in red. They're after the arrow. The reactants before the arrow, products are after. Sometimes you're given word equations. We learned how to write our formulas for our compounds, and sometimes if we're given the words, or you're hearing somebody say, hey, we have acetic acid plus sodium hydrogen carbonate, and that produces sodium acetate and water and carbon dioxide, you're going to have to translate it from the word equation that you're given. So here it is translated, and the chemical equation will tell us exactly what elements and in what quantity react. And that's important because whenever you're doing an experiment yourself, if you know what you're starting with, you can predict your products by knowing some basic chemistry. And so what you would do is you would set it up, and if you recognize the type of equation and you say, oh, this is an acid-base reaction, now that I see it written out, I can tell that this is an acid-base reaction. And acid-base reactions always have a salt and water, and sometimes carbon dioxide. But that's the importance of recognizing chemical equations. And it's important to know exactly what elements and in what quantity react. Now, there are symbols used in chemical equations to indicate whether something is a solid, in an aqueous solution that's dissolved in water, is what aqueous means, a liquid, or a gas. So for a reaction that absorbs energy or has energy added to it or released, you will see the word energy sometimes written with reactants or heat. So here is an example. We have water, and it's in the liquid form. That's what the L means. Plus energy produces hydrogen gas and oxygen gas. This is hydrolysis. You are separating the hydrogen from the oxygen. And it's important to know what it is that's going on. This is basically your recipe. You don't want frozen water. You don't want steam. You want liquid water. So this is why we have it. The more information you have, the more likely we are to be successful. Now, sometimes we release energy. Like I said, it would be on the product side as energy, just written. And it's important to remember that energy isn't always written in an equation. We've talked about laws, and we know that laws help us to predict outcomes. And when we balance chemical reactions, it's really important to remember the law of conservation of mass. This states that the mass of the products is always the same as the mass of the reactants. Matter can be neither created nor destroyed. Atoms don't change in a chemical reaction, we're just rearranging them. So we have the same number of each kind of atom in the reactants as we do in the products. With this equation, sodium hydroxide plus carbon dioxide produces sodium carbonate plus water. We're looking at it and we have to determine, is it balanced? Let's see. The law of conservation of mass says that you have to have the same amount of each type of element on each side. So if I look, I have one sodium and I have two sodiums on the product side. That's not balanced. We know our sodiums aren't balanced. We have one oxygen plus two oxygens for a total of three. We have 3 plus 1, that's 4. Our oxygens aren't balanced. One hydrogen, two hydrogens. They're not balanced. Carbon, carbon, 1. Only my carbons are balanced. So this equation isn't balanced. So how can we balance it? We do this by placing coefficients in front of the formula. And that will tell me how many units are involved. Coefficients are the big numbers out front. So if I put a 2 there, that means I have 2 carbon dioxides. If I put a 3 out here, that means I have 3 sodium hydroxides. It gets distributed to each element. So I would have 3 sodiums and 3 oxygens and 3 hydrogens if I were looking at them individually. We cannot, under any circumstances, change these little numbers called subscripts. We cannot change those. If you change the subscript, you're changing the identity of the substance. So if I said I needed one more oxygen and I changed that to CO3, I no longer have carbon dioxide. I have a carbonate atom that I would need to put a 2 minus on. If I put a 2 here, that's no longer sodium hydroxide. So we cannot change the subscripts. We can only use coefficients by putting numbers out in front. We can change that way, no other way. By putting a coefficient, it's just changing the amount that we're starting with. We say, oh, it's like saying I need 2 cups of flour instead of 1. And and you change the recipe that way. You still have the same thing, but just different amounts. It's not saying, oh, I need 2 cups of flour. Well, let me go get the baking soda instead. That doesn't work because it isn't the same ingredient. To balance equations, you must observe the law of conservation of mass. You will identify the elements on the reactant side, count the number of atoms of each type in the reactants, and then you look at the product side and count the number of atoms of each type in the products. Are the 2 sides equal? If not, you're going to change the coefficients. You'll count the numbers of atoms on each side again to ensure the equation is balanced. Let's look. Which of the following is a balanced form of the equation? So if I look, I say, well, here's this equation. We need to know which one's balanced. Well, here I have 2 times 2. That's 4 hydrogens plus, or produces, let's see, 2 times 2 is 4 hydrogens. So this one's good. Plus 2 times 2, which is 4 oxygens. And this is 2 times 1, which is 2 oxygens. This one's not balanced. So let me look at this one. And if it helps, you can make a little chart. You can say reactants and products. And then you can label it like this. Some people need charts. And if you need charts, you're fine. No worries. Here with B, I have 2 hydrogens on the reactant side. On the product side, I have 2 hydrogens. I have 2 oxygens on the reactant side. The product side, I have 1 oxygen. This one isn't balanced. So let me come back and let's look at this next one. Since oxygen, since hydrogen. Okay, here on C, I have 2 times 2, which is 4 hydrogens. And on the reactants or product side, I have 2 times 2, which is 4. So 4 of those are balanced. Here, I have 2 oxygens on my reactant side. And over here, I have 2 times 1 is 2. So C is balanced. I want you to look at the next ones and try them on your own. And then come back and check them. We're doing the same thing. So let's look. Trying to change this color, but it doesn't want to. There we go. All right. So if we make our chart again, if that's easier, reactants, products, we have our nitrogens, we have our hydrogens. On this first one, we have 2 nitrogens in our reactants, and 2 times 1, because we only have 1 nitrogen in this ammonia. 2 times 1 is 2. So our products have the same amount. Let's see if we're this lucky for this first one. 3 times 2 hydrogens is 6. 2 times 3 hydrogen is 6. So this one we lucked out. A was balanced. Let's look at this third one. Which is the correct form? Which is balanced? All right. Make your chart. If you could do it without a chart, that's fine. If you're a visual person and you need the chart, that's fine too. Use whatever you need to help you stay organized. Either method is fine. So here in the first one, we have Na plus Cl2 produces NaCl. So here we have sodium, 2 sodiums on the left on the reactant side, and 2 times 1 is 2 on the product side. So those are good. Here we have a subscript that says we have 2 chlorines because it's one of our Hofbrinkels, our diatomic elements. We have 2 times 2 then, 4 chlorines, produces 2 times 1 is 2 chlorines. This one's not balanced because we don't have the same number of chlorines on each side. So let's look at the next one. Here we have 1 sodium and 1 sodium. And we have 2 chlorines and 1 chlorine. So this one's not balanced. So it's not B. Let's look at C. We have 2 sodiums here. So this is 2. And 2 times 1 is 2. So we have 2 in the products. We have 2 chlorines here. And 2 times 1 is 2. So we have 2. Just remember it distributes to each element. So C is balanced. If you have trouble, let me know. We're going to stop there, and I'll see you next time.